Good morning, everyone, and welcome again here at the COP26 Cryosphere Pavilion. So today is the day of ice sheets. We will talk all the day about ice sheets. And the second talk of the day is about Greenland's tipping point. Welcome of those that are here, of course, and those that are following us in Stockholm and Geneva. The first speaker of today is Twila Moon from the National Snow and Ice Data Center, and then Jason Box from the GEUS will give us an overview and an introduction about the Greenland tipping point. So the floor is yours. Thanks.
Thank you so much for the introduction, and it's I'm really pleased to be here, and we all hope that the many decision makers here are actively learning more about these environmental changes and thinking about the decisions they're making and the irreversible consequences that they are really making decisions about for us. My name Twila Moon. I'm primarily a glaciologist and work on the Greenland ice sheet and the contemporary changes there. So I wanted to talk today a bit about, you'll see I'm calling it here thresholds rather than tipping points. I think sometimes the phrase tipping points can give us a sense in our minds that there's sort of a peak that's met and then something very dramatic happens. But really these changes are something that we see progress, and you can have a 1 year that's worse, 1 year that's better, but it's more these trends that we see. And also there are some kind of vicious amplifying loops within the cryosphere system that we need to be conscientious of and think about what that commits us to as far as irreversible change, particularly irreversible on human timescales. So first, to get ourselves thinking about the ice across the world, in blue are where all of our mountain glaciers are located around the world. And you can see that we have land ice from pole to pole at all our different latitudes. And then we have the Greenland ice sheet in the northern hemisphere and the Antarctic ice sheet in the southern hemisphere. Greenland ice sheet, of course, sitting on the largest island in the world, and Antarctic forming its own continent. As we look at sea level rise today, though, all of these different elements of land ice are playing different roles. So here in the lighter blue, we have the world's mountain glaciers, and they've been contributing to sea level rise for a longer time. Beginning in the 80s through the 90s, we were seeing land ice loss in these smaller mountain glaciers, and we were already seeing that impact on sea level rise. The Greenland ice sheet was actually largely in balance through the 60s, the 70s, 80s, and early 90s. It was really in the mid-1990s that the Greenland ice sheet started to become a major contributor to sea level rise. And so today, the Greenland ice sheet and the world's mountain glaciers have fairly similar additions to sea level rise at this point. But of course, they have very different reservoirs of ice as far as what is possible for future sea level rise. And Antarctica today is a small contributor to sea level rise, but again, has the largest reservoir for what might come into the future. So as we look at this map, one of the things that I think is often hard to connect with is that we're looking at this flat view of the Earth. I'm from the United States. So I'm comparing here Greenland's thickness. So suddenly thinking about what does this actually look like in 3D? And the Greenland ice sheet reaches almost 3 kilometers thick in the interior. So about 30 statues of Liberty ground to torch stacked on top of each other. This is how we get these incredible masses of land ice in Greenland and in Antarctica. It's not simply this flat map view. It's that we have these incredibly deep ice sheets that are really pushing down that land beneath them. as we measure changes in the cryosphere, you'll hear us talk about gigatons. And I was actually just talking with a colleague yesterday that we haven't yet, as glaciologists, come up with very good ways of helping all of us to imagine the scale of change that we see for Earth's ice sheets. A gigaton is such an incredible number for us to wrap our heads around. And what I'm showing you here are 3 individual gigatons of water sitting in Manhattan. So you can get a sense of how tall they are, how wide. They're each of these roughly a kilometer by a kilometer. So 1 gigaton, 400,000 Olympic swimming pools. Again, numbers that are almost impossible for us to wrap our heads around, and we haven't yet even found the best way to help each of us imagine what this might be like. So you can keep this number, gigaton, this measurement in mind as we look at the changes happening in Greenland. So here we have measurements from a pair of satellites that are actually measuring the gravitational changes due to our loss of ice in Greenland. And we're able to take these measurements of how this mass is changing Earth's gravity in order to interpret how much mass we're losing from the ice sheet. So over here on the right, you're able to see this up and down as we gain ice on the ice sheet in winter, and then we lose ice during the summer. And so we get this seasonal increase and seasonal decrease. And then on the left here, you're getting a sense of how we're losing mass from the ice sheet and how that has added up over time. So you can see that actually we have perhaps some small gains in the interior of the ice sheet because as we're warming the atmosphere in this cold interior, it can hold more water vapor, it can produce more precipitation. So we can actually gain precipitation at these highest, coldest parts of the ice sheet. But as you can clearly get your idea here, we're losing much more around the edges. And at this point, we now lose ice all around the coastal region of the Greenland ice sheet. This loss has implications at many different scales. So as we're losing ice from the ice sheet, we're changing the shape of the periphery of the ice sheet. We're exposing new land. We're exposing new waters. We're also inputting fresh water into the ocean system. So we're seeing changes in local ecosystems. We're seeing fisheries is the largest industry in Greenland, and we see changes already with where fish species are in this geographic region as we see more northern Atlantic species moving further north. So the fishery locations around Greenland are changing. As we're inputting this fresh water into the ocean, we're also changing the character of ocean waters, their temperature, their salinity, and this influences how the motion of our ocean currents work. So we're putting cold, fresh water in here around the coasts of Greenland, and that's influencing how these large regional and global ocean circulation patterns move and influence climate in more distant places, like here in the UK, for example. And then, of course, as we're adding water to the ocean, we're also seeing the implications for sea level rise. And sea level rise can be a bit hard to wrap your hands around as far as kind of like a single occurrence around the globe, because it doesn't happen equally around the globe. So counterintuitively, as we lose ice from the Greenland ice sheet, the biggest impacts happen far away from the ice sheet. People in Greenland will be experiencing lowering sea levels, and they will be needing to adapt to a very different coastline. Whereas that water that we're losing from the Greenland ice sheet is going to show up much more distinctly at shores far away from the ice. And so it's those places that might feel kind of intellectually most distant from the Greenland ice sheet that are going to feel actually the largest implications of this additional fresh water into our oceans, and seeing how that plays out on their coasts. That plays out not only kind of here, as we can see coastal flooding, but we also get coastal erosion. We have inundation of saltwater into freshwater resources. And often our coastal infrastructure was not built to deal with rising ocean levels. So sewer systems, water systems, kind of water drainage systems are all challenged by these changes that are happening at our coast and our additional water into our oceans. We lose ice from the Greenland ice sheet in a couple of different processes. And what I want to talk about are some of the ways that we lose ice and some of the kind of vicious amplifying loops that are part of the physical processes of what happens on the Greenland ice sheet and how that encourages or discourages additional ice loss. So one of the way that we lose ice from the Greenland ice sheet is from surface melt. We gain ice on the surface of the ice sheet all winter long. Then, of course, we roll into spring. The Arctic sun comes up. We start to warm up the atmosphere, and we start to lose all of that winter snow, particularly around the periphery of the ice sheet. And you can see here we form large lakes on the surface of the ice sheet and large stream networks on the surface of the ice sheet as well. This is a satellite image of an area of western Greenland. And what I think you can see so nicely in this Landsat satellite image is the difference in what the surface looks like as it experiences melt. So over here on the far right, we're looking towards the interior of the ice sheet, where we have this really bright surface thanks to the winter's snow and that buildup of bright snow. Just like walking outside in a white t-shirt, that bright snow is much better at reflecting solar energy, and so it's much better at sending the solar energy that arrives at the surface back out into space and not allowing so much melt. But you can see here along the coast, as we lose that winter snow, we start to expose this much darker glacial ice. You can also see these almost black dots where we're forming lakes on the surface of the ice sheet. And so all of these are dark, and they're better at absorbing solar radiation and better at producing melt. And there's been research looking at kind of, well, what are these processes important for these dark regions? And what does that mean for how much melt we get in those places? And there are hydrologic changes that happen here. We also, the shapes of these snow and ice grains will change. And as they grow, they often become darker and not as good at reflecting solar radiation. And there's also algae that will grow along these peripheral areas in the summer. But even with these changes, in fact, it's simply this exposure of bare ice that produces the biggest jump in this change in reflectivity of the surface, something that we call albedo. So as this snow line migrates and we expose this bare ice, you can see that it's simply this exposure that is producing the biggest change in how we're either reflecting or absorbing solar radiation on the ice sheet's surface. And this is all related to one of these really important amplifying loops or feedback cycles. And this one has to do with the elevation of the surface of the ice sheet. So what you can see here is this is an elevation cross section of the ice sheet up here from D. And what you can get a sense is that in the interior of the ice sheet, the elevations are flatter. You know, I mean, this is hundreds of kilometers getting compressed here, but you can really get a sense that the slopes of this line are not nearly so dramatic in the interior. But as we reach the coasts, we reach much more dramatic elevation changes. And so as we're raising our global temperatures, we're saying, okay, now the air temperature at which we can produce ice melt has just gone up in elevation. And if we're very close to the coast, and we're in an area where here's my ice sheet edge, and first maybe this rise in global temperature was allowing an additional 100 meters vertical elevation of location where we experience temperatures that could allow surface melt. Well, if I'm in a very high elevation area here at the edge, I may not actually expose that much surface area of ice. But as I start to move towards the interior and my elevation is flattening out, as I'm raising that temperature over that vertical 100 meters, it's exposing much wider area of the surface here. And so as our surface of the ice sheet is lowering around the edge, it's coming in, lowering into areas where we can produce surface melt. And we're also seeing these bigger, flatter areas exposed to surface melt. And this produces this kind of vicious amplifying loop of having a lower and less steeply sloped surface that is able to be exposed to melting. As we expose that to melting, we're more quickly losing the winter's snow and revealing this very dark surface that's good at absorbing solar radiation and producing additional melt, which can further lower the surface elevation. So this is one of these vicious amplifying loops that comes into play as we see the transformation of the peripheral landscape of the Greenland ice sheet. Another way that we lose ice from the ice sheet is along the edges, as we lose the solid ice of the ice sheet into the ocean via calving icebergs. So while all of this ice is sitting on land, it's not contributing to sea level rise. But once it's added to the ocean, either as liquid freshwater or as solid icebergs, it's now adding to sea level rise. And where these glaciers, outlet glaciers, come and meet the ocean, they can be very deep. You may be just seeing the at the surface exposure of 20, 50, 100 meters of ice above the surface here, but many of these sit in fjords that reach hundreds of meters down below the surface. And it's in fact, they can be exposed to warm subsurface ocean waters, particularly below depths of 200 meters or so, where we can have these deep fjords that allow deeper, warmer water to come and access the edges of this ice. And that can help to eat away at the edges of the ice. And you can see here is a map of what ice speeds look like around the Greenland ice sheet. And all of these places with that darker blue, ice motion in Greenland can reach speeds in areas of up to 16 or 17 kilometers per year. So we sometimes think about ice as moving very slowly, but in fact, there are all of these points around the edge that are really conveyor belts, these fast-moving glaciers that pull ice from the interior of the ice sheet and move it out quickly to the ocean. This is a kind of a sense of what these glaciers look like, and you can see that we reach these faster speeds at the edge of the glacier as it's meeting up with the ocean. And there is a bit of a seasonal cycle in this speed and a speed up and slow down as we develop sea ice in front of the glacier during winter. And then we have a increase in speed during summer, but they are moving ice rapidly all throughout the year. And this gives you a sense of where this ice, where we're doing kind of the hard work of moving ice. So this is ice dynamics, simply means the motion and movement of the ice sheet, and discharge of solid ice or icebergs. And you can see on the West Coast, we have some of our fastest moving glaciers that are very actively moving. Remember, we took a look at a gigaton, right? So you can see we have a single glacier that's moving more than 50 gigatons of ice into the ocean every year. So they're just incredibly large landscapes. This one here on the left, Jakobshavn Glacier, it's more than 10 kilometers wide. So you can kind of imagine if you've ever participated in like a 5-kilometer running race and you were just like running that entire time in a straight line across ice, you'd just be running across the surface of this one glacier that's doing so much work. And what can happen is that we can develop something of one of these other sort of vicious amplifying loops in this system, where the edge of the glacier, here you can see that the ice kind of flowing down from the interior and meeting this edge of the ocean. And many of these glaciers actually sit in these deep fjords that get deeper as they move inland. And so if I'm thinning the ice because of surface melt, or perhaps it's getting melted at the end from a warm ocean, that can produce retreat in this glacier. And if the edge of this ice is retreating back into deeper water rather than it kind of retreating back up onto land, it's actually going to speed up its motion. And so what we can have is a loop in which the glacier is retreating, it's speeding up, and you can imagine, just like pulling taffy, if we're speeding up the front, we're pulling that ice apart more quickly, we're thinning that ice, and we're making it still more vulnerable to retreat. So we can produce this loop in which our glaciers are retreating and thinning and speeding up and able to keep this cycle going. But I want to talk a bit about some of the other ways that we see transformation of the Greenland ice sheet edge, because this kind of change in particular, where we see a retreat and a speed up and a thinning, it's not something that we can see happen everywhere around the ice sheet. So I spent some time trying to kind of suss out what are these indicators of the rapid reconfiguration of the ice sheet edge, and what do they look like around the ice sheet. And we spent some time gathering data from all of these different glaciers over here and asking about the terminus. So the terminus is simply that ice front at the edge of the glacier, and asking about what kind of changes we have in the terminus and whether it is advancing, which would be here on the right, or retreating. You can see the edge of the Greenland ice sheet is overwhelmingly retreating. We don't see any consistent or long-term advance on the ice sheet edge. And then we were asking about whether these glaciers are speeding up or slowing down. So in the top half here, they would be speeding up, and in the bottom half, they would be slowing down. And you can see there's actually quite a few that are retreating and slowing down. So they aren't participating in this kind of vicious amplifying loop I was just discussing. And that's largely because the topography of the land underneath the ice sheet is the primary thing determining what happens when a glacier retreats. If a glacier retreats into kind of higher land underneath it, even if it's still underneath the ocean, it's going to become more stable and slower. If it's retreating into deeper water, then it's going to become less stable and encourage retreat. So simply kind of looking at where we have water, you can see that we have these dark blue kind of areas where we have deep fjords that travel into the center of the ice sheet, but that simply doesn't exist everywhere around Greenland. We have a lot of areas where the topography underneath the ice in Greenland actually rises in elevation as that ice sheet edge retreats. So we can't simply say, well, is everything speeding up in Greenland? Because that's not how the ice sheet is showing us the rapid reconfiguration that's happening at the edge. So what do we see in order to notice this rapid reconfiguration? Well, luckily, we can see it, first of all. And this is, there was actually an incredible revolution in understanding ice sheets. Even in the mid-90s, glaciologists thought that Antarctica and Greenland would not change on timescales that were kind of relevant to our human politics. They imagined them as these big, huge blobs of ice just slowly transforming under the power of gravity. But thankfully, satellite technology developed, and we were able to actually look at the surfaces of these ice sheets and begin to take data that was at the scale of ice sheets. And we were able to measure the changes happening on the surface. And we suddenly saw, oh my goodness, these ice sheets are changing at incredible speeds that we could not possibly imagine before. And there we see glaciers that are doubling their speed in only a couple of years. And these were changes that previously had been really unimagined in the glaciological community. And you can envision how this discovery has revolutionized kind of the urgency with which we are studying and thinking about ice sheets. So there's now much more interest, there's much more participation in research, and thankfully it's meant that there's much more that we know about ice sheets and how they behave and how they can change. But our early satellites were just kind of like putting on like really fuzzy glasses. It was hard to see the places where the ice met the land. It was hard to see very slow motion on the surface of the ice sheet. But thankfully, technology has really continued to advance, and it's like we're constantly getting updates in our glasses prescription, so that today we can much more clearly see the behavior of the ice sheet as far as being able to see slow motion and being able to see the ice sheet slowing and being able to see these edge points. So what do these tell us? And I'm going to show you here a few slides that have these several pairs. So up here, you're going to see pictures of how the speed of this ice has changed. So here you see a glacier that's kind of exiting the ice sheet this way, and the red is going to show you areas where that ice has sped up, and blue is going to show you areas where that ice has slowed down. And then here you're going to see the topography underneath that bit of ice. So here you can see that the bottom of this ice sits on the land, but underneath sea level. And then over here, you're going to see just the kind of raw, how quickly is this ice moving. And so there are several different kind of indicators of this rapid reconfiguration that we can now see around the ice sheet edge. One of them here is this narrowing of fast flow. So it's a bit hard to see here, but there are a few blue lines at the end of this glacier that show you that this glacier has not actually done much as far as retreating over the last couple of decades. But nonetheless, it's started to change the way it moves, and it's starting to squeeze this ice into a faster river of ice flow in the interior. So we see these fast flow areas kind of getting concentrated and pushed through the more central flow location of these glaciers. Another change that we see happening around the edge of the ice sheet is that we're changing where we're moving ice. So here you can see, this is maybe a good one to start with. You can see all of these nice blue patterns where this is where we're moving the ice within these ice streams at the edge of the ice sheet. And you can see over here that we're starting to move ice more intently, and it's speeding up into this central outlet. But both of these outlets above and below this are slowing down. And so we're starting to route our ice into different places around the ice sheet. And somewhat related, we're also starting to see abandonment of different outlets. So whereas before we might have had very active ice motion associated with it, significant iceberg calving, for some of these outlets that meet up with the ocean, we're now losing those outlets, and we're kind of abandoning different points where we previously would have moved solid ice and connected it to the ocean. So these have some beyond kind of this transformation in the ice. This also has some interesting implications for water in this system. So we have a multi-decadal change in ice flow. This is simply another way of looking at the speed of motion. With these red colors are showing fast motion. And you can see here, for instance, we had an area where we had fast motion on one glacier. That glacier has significantly slowed, and we have now faster motion at this other glacier below. But the edge of the ice sheet is not just ice. Every summer, there melt forms on the surface. We get large melt lakes forming. We get streams. All of this melt actually travels through the ice sheet, underneath it, and then travels below the ice. Much of the area of the bottom of the Greenland ice sheet is actually liquid water between the ice and the land below it. So it's not frozen to the land below it. And we move this water underneath the ice sheet and then out into the ocean. And along with that speed up, we can now look at information telling us about the thickness of the ice sheet and how that's changed. And you can see here that there have been areas where we're thickening the ice sheet, where it's slowed down, but significant areas where we're thinning the ice sheet. So we see changes in motion, but we also see this kind of overwhelming thinning and lowering elevation around the edge of the ice sheet. And these kinds of changes in the thickness and the motion of the ice sheet translate to changes in the hydrological network of the ice sheet as well. So we can see these blue lines are not surface water motion. They're water motion underneath the ice sheet. And you can see that we've transitioned from a time when we would have moved all of the meltwater of this section of the ice sheet into the northern fjord, and that fjord would receive this cold, fresh water. And now we're at a point where all of the surface meltwater that's occurring from this section of the ice sheet is getting rerouted to an entirely different fjord area. So we have not just a transformation of the ice sheet itself, but a real transformation of the coastal ecosystems and coastal environments around the Greenland ice sheet. And of course, this is important because, oops. Let's see if I can get this to go. I think I'm a bit stuck. Fantastic. This is important because as kind of demonstrated here, this is where we have the ice sheet meeting up with the ocean. And this can be areas of deep, deep water, many hundreds of meters of deep. And we are getting this meltwater that's coming out here into the edge of the fjord. And of course, it's not just the physical system. So this cold, fresh water might influence the salinity of this fjord, influence how icebergs are melting. But of course, this fjord has fish, it has narwhals, it has whales, it has polar bears, it has all of these kind of marine mammals and elements of the local ecosystem that the people of Greenland depend on for subsistence hunting, for their food, for the major exports of the Greenland economy. And just to give you a sense of why it might be important that this fresh water here is entering out at different places. One thing that can happen, for example, is if this water is entering a fjord that is particularly deep, that water, that cold, fresh water, it might come out at the bottom and underneath the glacier, and it might entrain a lot of rich nutrients that are in the lower part of this water column. But if you're in a very, very deep fjord, that water is going to entrain all of these nutrients and it's going to start to rise, but it's not really going to get an opportunity to rise up into the photic zone where we have all of our primary productivity. So it's entrained nutrients, but it hasn't really managed to deliver it to the kind of ecosystem region in which those nutrients would be used. But if this water was suddenly now entering this landscape via a different glacier, coming out perhaps an outlet that's just in a different location in this fjord, it might not be so deep, and it might still entrain nutrients from the bottom of the water column and have the opportunity actually to bring those nutrients up into the photic zone and really influence the primary productivity in that fjord. So it's not simply that we're adding cold, fresh water, but it's also where it's being added and how it's transforming the ecosystem of that fjord. And this, of course, has huge influence on what people are able to catch, what they're eating. This is one of my Greenlandic colleagues you can see is, happily spending his time eating fish, whale, and these sorts of things, and the major industries of Greenland. So, as I wrap up here, I just want to really emphasize that these are changes in the Greenland ice sheet that are coming, whether we follow low emissions or high emission scenarios. Now, granted, there's a very, very big difference between those two endpoints. High emissions will bring us much more rapid transformation of the edge of the Greenland ice sheet. I'm showing you here a scenario that is following a low emissions pathway that I certainly sincerely hope that our decision makers here at this meeting are doing their darndest to negotiate for, because even under this change, you can see all of this purple along the edge is newly exposed land. So even if we follow these low emission pathways, we still need to be preparing for, planning for, and responding to a reconfigured coastal ocean and landscape around Greenland, and also a reconfigured landscape around our coasts around the world that will be influenced by these losses for the Greenland ice sheet. So a simple reminder, this helps to give you a sense of what this means for the long term as well. So many of our discussions here stop at 2100, but ice sheets respond over millennia. And the changes that we're going to create in the ice sheet that are responding to our missions of this decade are going to be irreversible on human timescales, and they're going to lead to incredibly different landscapes even 1,000 years from now. The Greenland ice sheet has had ice existing there for hundreds of thousands of years, but we're in a place now where if we were to slide back, we might put into place a process in which we're losing the whole ice sheet over the next 1,000 years. As a glaciologist, I find this completely inconceivable and kind of a future in which we I don't imagine I could get any sleep imagining that this is happening, right? But if we take strong action, if we focus on a future in which we're lowering our emissions, we're going to see a transformed ice sheet, but we are going to keep an ice sheet. We're going to have a place that is going to be able to help sustain the animals, the plants, the people, and the cultures that are all dependent on this landscape. So I just can't emphasize enough that the decisions we make now, we may not be able to immediately see their impact, but in fact, their impact is going to be felt truly for millennia. This is a responsibility and a power that I think is almost inconceivable that we have arrived at this time, but nonetheless we have, and I hope we can take it really seriously. Thank you.
Thank you very much, Twila. There is maybe some time for some questions, maybe from the audience. Raise your hands. Okay, can you come here?
Hi, thank you so much for the really interesting talk. Very near the beginning, you showed a graph of the decline over time, but I noticed between, I think, 2016 and 2018, it sort of flattened. What was the cause of that?
Yeah, this is a great question. I'm glad you noticed this detail. That was actually a gap in data. So this data in that figure is a combination of data that came from what's called the GRACE satellite, and then a replica pair. GRACE is actually 2 satellites that work together, but then there was a replica pair of satellites, and those GRACE follow-on satellites didn't become operational in time to overlap with GRACE. So we have a short period of this gravity measurement data that's missing. There are other ways that we estimate and measure changes in ice sheet mass. So there is other information, but for that particular data type, there was a gap in data. And I think it speaks to how important it is to kind of pay attention to what instruments we have working and how they can continue to work with the next generation of monitoring instruments too.
Are there any more questions? If not, I have one. It's just a curiosity about the processes that can lead to the melting of the overall Greenland ice sheet. And my question is, considering that under a global warming scenario, there will be much more wildfires, for instance, like let's say in northern Canada, etc., how these can affect the melting of the glaciers through the transport of black carbon particles, for instance?
Yeah, this is an important part of understanding ice sheets as part of the global system. And we can see that black carbon, particulate matter from wildfires can be transported and deposited on the Greenland ice sheet. And certainly any of these kind of processes that help to darken the surface of the ice sheet do make it easier to produce surface melt. And so that becomes that kind of stark difference between sort of our fresh snow, and then of course as you're melting that snow, you're depositing anything that fell on the surface, and it's getting concentrated on the bare ice glacial surface and helping to darken it. And Jason Box, who speaks next, I suspect might say a few things about kind of that transformation of the ice sheet surface too. But this is an important element and part of thinking about ice sheets as part of the global system, and how they are also going to be influenced by these changes, such as increased wildfires that are coming with climate change.
Thank you very much. And if there are no more questions by the audience, I am glad to introduce the next speaker. So Jason Box from the GEUS. And so the floor is yours. Thanks.
Hello, everybody. I'm a professor in glaciology and climate at the Geological Survey of Denmark and Greenland, and I want to talk about the physical mechanisms behind this tipping point for Greenland. And an important frame is the fact that the Arctic is warming 3 times faster than the rest of the globe. This Arctic amplification, driven, of course, by stunning spikes in enhanced greenhouse effect. We're at 50% above pre-industrial carbon, and the land ice is having its delayed reaction to this abrupt impulse. This 3D rendering of Greenland presents it as a dome of ice resting on land. And this tipping point that we're talking about involves something called the elevation feedback. And on the left, you see the elevation profile with the ice dynamics moving the ice through the system. You see the colder atmosphere above. And in a thinning scenario, what you end up with the shape of the ice sheet is a much larger area exposed to this higher temperature. And this presents an amplifying feedback as the ice sheet draws down into warmer parts of the atmosphere. This amplifies the warming. This is the tipping point. This is the irreversibility for the ice sheet. The black line illustrates how the area of ice increases non-linearly with elevation. That's what you saw in the previous slide. To reinforce, this is a non-linear mechanism. Greenland is by far the largest land ice contributor to sea level rise. the blue area is the ice sheet itself. There's a red wedge at 6%, meaning that 2/3 of Arctic land ice contributions to sea level come from Greenland. And Arctic ice in the amber curve is much larger than the contribution from Antarctica on the lower curve. But what's more important is that all of these curves have been increasing their sea level contribution in each following decade. That represents an acceleration, which makes it very difficult to project this into the future. And I'm going to talk about why the ice sheet models are essentially unable to give us a high fidelity projection into the future. To familiarize you with the bare ice area, you have water saturated snow, the blue areas absorbing more sunlight, and the impurity rich bare ice absorbing much more sunlight. The sunlight absorption is by far the largest contributor to melt energy. So this expansion of the bare ice areas is one of the amplifiers, one of many amplifiers that I'll talk about. And this is to illustrate how it takes a long time for the ice to accumulate, but the ice can break away in a matter of minutes. And on an earlier slide, you could see that sea level during the ice ages gradually decreased during the several ice ages because it took millennia for the ice to accumulate on land. Well, the sea level then it rises abruptly as we exit the ice ages because, as you can see here, this 900-meter thick iceberg breaks away in a matter of minutes. So the ice is lost much faster than it is accumulating. And to tell the story, it's useful to use this narrative device, follow the water. It's kind of like in politics, you want to understand what's happening, you follow the money. Well, if you want to understand what's happening on glaciers, you follow the water. And as you saw before, water-saturated surfaces absorb much more sunlight. These are solar collectors. This is 1.5 kilometers wide, 30 million cubic meters solar collector. This factor is not in the climate model projections. All of these lakes essentially drain into the ice at some point during each melt season. So they deliver 0 Celsius water into -10 ice sheet interior through infiltration. And that infiltration means that heat is being delivered to the ice internally. And that internal heating produces softer ice because warmer ice can deform more readily. As you can see, the water eventually makes it to the bottom side of the land ice. And that's where it comes out, it rushes out. It entrains sediment, and you can see the muddy water that's right up at the front of the glacier because this fresh water is lighter than the salt water. It immediately rushes upward. This effect, like the one before, the melt-induced acceleration is not yet in the ice sheet models used to project future sea level rise. The ice, the water that's coming out is extremely turbulent. So this is a forced convection heat exchange, much more efficient than just warm water in contact with the marine terminating ice. This illustration shows how it's typical to have a +4 Celsius Atlantic layer at depth. And this is right at the grounding line where the water comes out at the bed and entrains this warm water and forces a heat exchange right at the front of the ice. So as the ocean warms, delivers more of this strongly melt-inducing warm water. This ensures the connection of a warming ocean with the ice sheet. Yet another factor is hydrofracture, the fact that liquid water is heavier than ice. This water, when filling depressions, it exerts a greater force at the bottom of these cracks, and provided that the rifts here are kept full with water, that ensures that will cut open ice shelves. And this is precisely what happened on the former Arctic's largest ice shelf in northwest Greenland in a record warm summer. The rift here was water flooded, and we had 3 times Manhattan Island area breaking away. 2 years later, another then new record warm summer, we lose large areas of the site. So the hydrofracture mechanism, yet another not included in the models used to project ice sheet contributions to future sea level rise. South Greenland, all around the ice sheet, at the margin, you see this dark ice. You see the stripes. What's causing the darkness? Why the stripes? Under conditions of prolonged sunshine, droughts, which are occasionally happening in longer duration because the weather systems are becoming more stationary as climate unravels, you get really dark surfaces like this, where the surface is absorbing 4 times more sunlight than it would with a pure bare ice surface. And this was an instance where there was 6 weeks of sunshine. And for some reason, the surface got so dark. This is down in the lower parts of the ice sheet. Why was this happening? When you sample this material and look at it under a microscope, it's biological. Microbial darkening. These microbes regulate photosynthesis to do their life cycle, and they produce the darkness. The dust particles, you can see they're translucent. This is quartz, but it contains nutrients that the microbes need. This is yet another factor not in the climate model projections for sea level rise from ice sheets. It's a climate X factor because we still don't know if pollution is fertilizing them, and we don't know how high on the ice sheet they will colonize. We do have reconstructions of the ice sheet. This one's very interesting, more than 100 years long, and you can see the recent accelerating loss of ice. And then in between the 1960s and 80s, the ice sheet was stable. There's sufficient evidence to convince me that was due to sulfate cooling, so-called global dimming. This was from the burning of coal in the atmosphere, and as we transition off of coal into cleaner coal and less coal, we have an aerosol unmasking, and that will enhance the melting on Greenland. The removal of the aerosol masking effect is one of the very alarming aspects of having cleaner energy. Here's a river system that shows that the temperature on the coast produces a nonlinear increase in runoff through this river system. It's actually to the 3rd power, so it's an extremely nonlinear sensitivity. So that's one of the main messages here is these nonlinearities make it very difficult for us to conceive in our minds just how responsive, how sensitive, how quickly the ice can go. Another measurement-based study finds a similar conclusion where there's, again, a sharp increase in melting based on temperature. This means, of course, that as Arctic continues warming faster than forecast, that we can expect a very sensitive response of Greenland ice. We had a stable period of sea level, 6,000 years, under which civilization developed. And what we face in the future is somewhere in between those two curves. The lower constant 1990 emissions is behind us in the rearview mirror. The business as usual scenario, it seems unlikely. We may essentially crash the climate before we can even possibly burn all of that fossil fuel. So the truth is somewhere in between. But as you can see, the expected sea rise in the coming centuries is absolute catastrophe. Can we slow this down? I think that's what hopefully the leadership at a meeting like this can get this kind of a message and get busy with the monumental, enormous task of not only reducing carbon emissions, but somehow removing gigatons of carbon from the atmosphere. The era of abrupt sea level rise is upon us. I'm sure that we face other more immediate challenges through the loss of water and food security. At the moment, we're not running for the hills, but it's time to start walking. And to kind of try to sum up, the Arctic climate was actually cooling. We were heading for another ice age, but due to industrial output, we entered an era, the Anthropocene, where we shoot out of what should have been the next ice age, which would have been very difficult, but we've gone far off into the unknown. And the projections of the future, brace yourselves, they're like this. The Paris scenario is the lower curve, and the business as usual is the upper curve. This is what negotiators here need to make sense of. What is at risk is basically a governable society. Thanks for your attention.
Thank you very much for this very nice presentation. And so there is time for some questions from the audience here. Yeah, please.
Is this working?
Yeah.
With the it's not working. Is it working? I don't know. It's not working. Okay. Yes. So a question about the melt rates of Greenland. What you would expect? How much you would expect them to increase when we lose the Arctic sea ice? Say we lose the Arctic sea ice in 5 years for a month, and then a few years after that, it's gone for 3 months or 4 months of the year. How much will the rate of melt on Greenland increase as a result of that loss of sea ice?
Yeah, in the last 50 years, Greenland melt has doubled. And as we lose the ice in the north, there's already evidence that the largest warming around Greenland in the last 50 years is in the north. And it's the reason why the Arctic is warming 3 times faster than the globe. It's the loss of Arctic sea ice. So we're already seeing increases in melt in the north. And as the sea ice retreats across North Greenland, we will see the most warming there. And presumably, predictably, that those now kind of ancient, steady, non-accelerated glaciers, those too will accelerate. And one of them is the largest ice stream that has some underwater bed that goes into the deepest parts of the ice sheet.
Many more questions? Yeah, please.
Thank you very much. That was absolutely fascinating. In terms of some of the water issues that you raised and that you said are not fully accounted for in the models, is that a question of more observation and more science, better models, better computing power, and are there any projects in place to improve those models at the moment? Thank you.
The modeling community has been making big advances. However, due to coarse resolution in the global climate models, it to some degree, it's not even the fault of the ice sheet models. It's the fact that the ocean projections lack the resolution to resolve the narrow ribbons of warm water that get into the fjords. And the atmospheric models don't yet resolve these highly amplified waves that produce extremes like the record warm Pacific Northwest heat wave, for example. So that's just the problems in the atmospheric models. Then the ice sheet models, they struggle with the iceberg calving physics. They're like the atmospheric models. The ice sheet models are full of so-called parameterizations, which are facsimiles, approximations, kind of computer time shortcuts that are necessary because the models are being run kind of state of the art, but they're just unfit for the task at the moment, which is why the discussion remains about the so-called long tail of ice sheet decline. There is a low probability yet high impact possibility that's still very much plausible, and my opinion is that the chances of extreme sea level rises are something that should be taken extremely seriously, because it's very much in the cards.
I also invite people from Geneva and Stockholm that are following us to type the questions in the chat box, if any. Otherwise, okay, one more question, please.
I got the impression towards the end that you were at least perhaps hinting at, even if we stopped our emissions of carbon dioxide, let's imagine by 2040, 2050, that the level of CO2 in the atmosphere and the level of warming we actually got would actually lock in significant ongoing sea level rise for some significant time to come. So are you really saying that if we are serious about stopping some of the worst impacts of climate change, we are going to have to remove absolutely huge quantities of carbon dioxide from the atmosphere? Mitigation simply is not enough.
Yeah, and I might go further that because the oceans have been absorbing so much of the heat imbalance of the planet, even were we successful in removing hundreds of gigatons of carbon in the atmosphere, we would still be looking at a destabilized Antarctic ice sheet. And as you saw from the shocking kind of boomerang-shaped curve, even in the Paris scenario, Greenland will remain beyond its threshold of viability. So it's a matter of time until the elevation feedback, the drawdown, this tipping point of Greenland becomes irreversible. The good news is any brakes that get applied now will slow that process down, buying time and saving lives.
Okay, so thank you very much, Jason, again for this incredible presentation, and thanks to all of you. And so I invite you to come here again at 1 p.m. because the session Ice Sheets and Sea Level Rise will continue this afternoon. The title of the talk will be Antarctica and Paris Goals, Risks of Massive Sea Level Rise. And the speaker will be Rob De Conto from the University of Massachusetts. So you are welcome here at 1 p.m.